Namaste. Okay, I wanted to do a quick video to explain something to you guys that most people don't really understand. And that is, you've been taught since you guys were little kids, it's a scientific fact, that near the Earth's surface, all objects fall at the same rate. And in previous videos, I taught you that, and you probably even learned in the middle school and elementary school, that the rate at which they fall near the Earth's surface is 9.8 meters per second squared, which means that every second you fall, you get faster by 9.8 meters per second. And that's neglecting air resistance. Okay, but the question is, why is that? Because doesn't it make sense that if you have a brick and then you have a feather, that if you drop the two, the brick is going to fall faster, the feather's not. And that's why for the longest time on Earth, just like we thought that the Earth was flat, we thought that objects didn't fall at the same rate, because that's just not what people observed for thousands and thousands of years. We observed that objects fall at a different rate. We see in the fall, we see the leaves fall from the trees and they kind of gently fall down. All right, yet if you chuck a rock off a high place, that falls pretty quickly. And the thinking was, well, it's because the rock's heavier. Heavier objects fall faster. So why is it? All right, well, I want you to take notes on this, because this is really an example of really, really good thinking. And I'm going to tell you about the guy who in our culture kind of broke through that conventional thinking that objects that are heavier fall faster. And the guy's name was Galileo, and he lived about 500 years ago in Italy. And the thing about Galileo was, he was one of the first Western scientists, all right? By Western I mean our culture. And he didn't have, 500 years ago, he didn't have a lot to work with. He didn't even have like a clock to time. There was no stopwatches, anything like that. Let alone like the things we have today, like laser motion detectors and all these instruments that we have that we can measure stuff very accurately with. Radar guns, so you can measure speed and distance with really great precision. He didn't have anything like that, but he did have a brain, and he did use it. And here's what he thought. So the first thing I want to say is he said, okay, well, let me try this. What if I went with the wisdom that we have that a heavier object would fall faster? So wouldn't it be true then that if I took a heavy object, and I'll put a big letter M in there for big mass, and I took a smaller object, and again, make sure you're writing this stuff down. This is kind of important. And again, most people know, they were taught that objects fall the same. They don't know why, okay? So I'm going to teach you why right now, all right? And most adults don't know what I'm about to teach you, okay? So anyway, so he said, all right, so what if I have a smaller or a big object? Wouldn't that fall faster than the smaller object? Why? Because a previous smart person, many centuries before Galileo, even before the birth of Christ, about 3 centuries before the birth of Jesus of Nazareth, so in about 300 BC in Greece, there was a man named Aristotle. And Aristotle was a philosopher, not really a scientist per se, because a scientist tests things out. A philosopher kind of thinks about it. But Aristotle never took the next step, which was to test something out. Galileo was a scientist because Galileo would think about things and then he would test it out. He used the next step in the scientific method that we use today. And so Galileo thought, well, like what Aristotle thought, that it's like, okay, well, what if I have this big heavy object and then a smaller object? Then the heavy object should fall really fast and the smaller object should fall just a little. Why? Because it's smaller. And Aristotle said it fell less or slower because it's in the nature of smaller objects to fall slower, and it's in the nature of a larger object to fall faster. But Galileo said, well, what if I did this? And this is an example of really, really good thinking. Okay, and he said, well, what if I did this, and if I took the smaller object and I tied it with a rope to the bigger object? Now what would happen? Now we have essentially a combined object of the bigger mass plus the smaller mass. So what would it do? Would the combined object, because the two objects are tied together now, so don't they have more mass? So wouldn't the combined object fall even faster than just the bigger mass by itself? Or wait, what would happen? What would this happen? The smaller object, because it wants to fall slower, because as Aristotle said, it's in its nature to fall slower, would it kind of hold the larger mass back, and so the combined object, would it fall slower than if you just drop the big object by itself? And that's a really good type of thinking. And he came to what's called, the conclusion's called a paradox. A paradox is a contradiction in logical thinking. Because you see, the way we're thinking here, we're not really saying anything wrong according to Aristotle's theory, what Aristotle thought, or his theory. We're just kind of going with his theory, and then when you do, you kind of arrive at this kind of paradox. Would the combined object fall faster than just the heavier object, or would the combined object fall a little bit slower than the heavier object, because the smaller one is holding it back a bit? Okay, so what Galileo came to conclude then is that, you know what? They would both fall the same. They would both fall and speed up at the exact same rate. And there's another factor going on, and that factor would be air resistance. And the reason why we see lighter objects fall slower is because the air affects them more than a heavier object. Okay? And then what Galileo did was he went and tested it out. And so his famous experiment, one of his famous experiments, was he went to the Leaning Tower of Pisa. So you got this tower and kind of like that. And then he would have some guy go up to the top, and he would hire some guy to drop cannonballs of different sizes, like a large cannonball and a small cannonball. And the guy would take two cannonballs and put them on like a board, a plank. And then when Galileo gave him the thumbs up, the guy would just go and then drop them over the side. And they chose cannonballs. Why? Because of their spherical shape, they're not affected by air resistance over a short, like 100-meter drop or something like that. The air is not going to affect either the small ball or the large ball in any appreciable amount. So that's what he used. And then he did a bunch of observations of this, and he noticed that the two balls would hit the ground at pretty much the same time every single time, the small ball and the large ball. And so that was Galileo's big experiment. Okay, so all right, great. So he tested it out, and he found out that objects fall at the same rate. All right, and so the question is, though, but why essentially is this? Okay, well, here's the reason. Okay, gravity is a force, which I'll write as the letter F, and we know, all right, that forces cause things to accelerate, and you saw in the other videos what acceleration is. Acceleration is a change in speed. Gravity, the way it does it is its force causes objects to accelerate by speeding up. Okay, great. So forces cause an acceleration, and the bigger the force you have, the more acceleration you get. Now, something else is affected by forces, all right, and that's, whoops, let me write it like this, and that's the mass, okay, which I'm going to write as the letter M. So M stands for mass. And the reality is that mass has an effect too, because it takes a larger force to make a large object accelerate than a small object. And if you ever want to test this out, go in your house, go dig up your old toys from when you were a little kid and find like your little toy car or something like that and just push it. And you can push it pretty easily. And then go to your parents' car, all right, and put it in neutral and try pushing that. Make sure your parents know what you're doing before you do that. But you're going to find out that it takes a lot more force to push an actual real car. Why? Because the mass is bigger. Now I'm going to rewrite this. And the way you say this mathematically is that the acceleration of an object, all right, is, now listen to my language because it's important that you know language. is proportional to the force you put on it. So in other words, if you push something more, it accelerates more. If you push something harder, it accelerates more. But it's inversely proportional to the mass, and that's why that's on the bottom of the fraction here. What does that mean? That means the bigger the mass gets, the smaller the acceleration for a given force. So the big car is, if this is a big number down here, this is a smaller number up here. The larger this number gets, the smaller this number gets. So the bigger the car, the harder it is to accelerate, the more force you need to get it to accelerate. So it is actually true, and let me do this so you'll have a little more board space, that if you have a big mass, and we know this, so here's a big cannonball, and here's a small cannonball, it is actually true that gravity pulls with a bigger force on the larger mass. It just does, okay? Masses create gravity, and the bigger the mass, the more gravity you get. And we know this because we're next to a very, very big mass compared to us, and that's the planet that we're standing on, okay? A small mass, gravity doesn't pull on as much, and so it has less of a force of gravity on it. And I'm going to draw that as a little f, and hopefully you can see that better. So little force of gravity on the smaller mass, bigger force of gravity on the larger mass. But then again, why do they fall at the same rate? Well, because it takes a bigger force to move the larger mass. And you don't need as big a force to move the smaller mass, so the acceleration evens out. So the force on this and on the bigger mass gives it acceleration, but it evens out with the smaller force on the smaller mass. So the acceleration for both cases winds up evening out and being exactly the same. Now you know this, you've seen this, something like this in the past, because you were taught by some math teacher that if you take a circle, there are different parts to a circle. The outside of the circle is called the circumference. And I'll write that as a big letter C. And if you drew a line straight across the circle, that line is called the diameter of the circle. And it was figured out a long time ago by the Greeks that if you take the circumference of a circle and you divide it by the diameter, you get a very special number. And that number is 3.14, which is given a special symbol, and that is the Greek letter pi. Pi, which is like two sticks with like another, I don't know, one across them or like that, is the number 3.14. And it works for all circles, so that means if I have a tiny little circle, and it has a little circumference, and it has a smaller diameter, it still works out that if I take that little circle and divide its small circumference and divide it by its little diameter, and I divide those two numbers, I get the exact same number, 3.14, which is pi. So the circumference and the diameter on the big circle, when you divide them, it kind of evens out with the smaller circumference and the smaller diameter on the smaller circle. And when you divide them by each other, for each circle, you still get the exact same number. And that's why it's a very similar case here with the masses, okay? That if you take a big mass and you take the force of gravity on it divided by its mass, you get its acceleration, all right, due to gravity. And if you take the smaller mass and you take the smaller force of gravity on it divided by its smaller mass, you get the same acceleration. And what is that acceleration? Well, on Earth, that acceleration is 9.8 meters per second squared. So for all masses on Earth, due to the Earth's gravity, all right, the force that the Earth pulls it with divided by its mass still winds up being the same exact acceleration for every single mass. Every rock you drop, all right, every leaf that, well, not all leaves that fall because there's wind resistance there, but neglecting air resistance, if you take the force of gravity due to the Earth divided by its mass, you get the exact same acceleration for every single object in every single case. And on Earth, that acceleration is 9.8 meters per second squared. Since we're Americans, and if you're like me, as an American, I don't think in terms of meters all that well, but I think in terms of feet a lot better. If you take if you did it in the English system of units, 9.8 meters per second is exactly the same acceleration as 32 feet per second squared. So you could say that you get faster every second you fall by 32 feet per second. You speed up by after every second that you fall. And that is why objects actually fall at the same rate. Now I'm going to put on there a video of two. What they did was they went to the largest vacuum chamber in the world, which I believe is like in Cleveland, all right, and it was built by NASA to test out spacecraft and things like that. And it's basically like a big 3-story cylinder that they can shut off and they can pump all the air out of. And so what they did was in the experiment, I'm going to attach this to the lesson on Classroom, and it's cool to watch, so watch it, all right? And what they do is they haul up a bowling ball and some feathers, and they have a little electronic trigger up there, and they leave the air in there first, and when they drop them, you see the bowling ball just shoot down, and the feathers kind of float down, just like you'd expect. But then they pump the air out of the room, and they do the same thing. They bring the bowling ball up and the feathers, and they bring the air. They take the air out of the vacuum chamber, and then they drop it. And you see the bowling ball and the feathers falling exactly together, just the way Galileo predicted, and just the way we know things actually work. Okay, so check that out. All right, so now you know something that most adults in America, and in fact the whole world, don't really know. You know why all objects fall at the same rate, because the forces and masses on them even out to exactly the same number, 9.8 every single time. Okay, so, all right. Good luck with the problems I give you and the work I give you, and see me during my office hours. Goal us out, and remember to enjoy your apocalypse.